All right, thanks, Elise. So, my name's Alex. I'm an electrical engineer here at Yale, and Elise talked about all the really cool things the eye can do. It allows us to see the world, interact with it, and we can even see individual photons. But I'm an electrical engineer in the 21st century, and I know there are really cool things we can do digitally. I'm going to talk about some of the ways we can engineer a better eye and kind of even go beyond just seeing things. So, one of the really big drawbacks of the eye is that you can't share what you have just seen. You have to describe it to someone. To kind of illustrate this, we're going to show a clip from the 2014 Winter Olympics. This was in the men's biathlon, had one of the closest finishes in history. You're going to see the guy in black is going to be racing against the guy in white. I want you guys to think, who won this race? Whose boot crossed the finish line first? They're racing. The guy in black starts celebrating. The guy in white just tries to squeak by. Who won? Let's take a closer look and find out. So we zoom in. You see guy in black, his boot crossed first. Let me zoom in right there. So we know exactly, because of this image, the guy in black won this race. Now your eye can't capture this moment. It can only passively see it. It can't stop it in time, whereas a camera can. So to kind of think about how we might design a camera in reference to our eye, we're going to look at the eye in terms of kind of a machine. What is it doing? So we have some light coming in, hitting the back of our eye, here showing this little curve, and it sends information down the optic nerve, which I'm showing here in red. So we're going from light, our detector, which is our eye, to information. So the light will first hit the detector, and then our detector will then send the information into your brain via this optic nerve. So we're thinking about, what is the eye? What is it actually doing? First it has this lens, which just focuses the light into the back of your eye. Then it has these rods and cones, which are really good at recording the light in the way Elise described. And then the eye will store the light and send it down the optic nerve into your brain. Now, if we're going to design something else, we're going to do those same three things. This is exactly what a camera is doing. First, you have a lens in the front of the camera that focuses the light. And then you record the light on a piece of film, or we're going to learn to be a CCD. And then we can then store the light in some sort of photograph or some sort of memory on your camera. So in the same way, we saw our eye as a detector because it will then interact with some light and then send the information to your brain. Our camera is a really good detector because the important thing is that not only will it record the light, but you can save the light, what we call a photograph. What's different is that the light's going to hit our film, our detector, and then the detector will store the information instead of just passively recording it. So let's think about how this original film process started. So if we start our original image, just a really simple thing of a white lamp on a black background. And remember from Elise, this lamp is producing a lot of photons, which are shooting back into your eye, or in this case, back into our camera. And because of all these photons, the lamp looks very bright. So we image this onto some film. And this film is the brown outline I'm showing right here. And this film has all these chemicals on it. They're photosensitive, which means that you have these original chemicals in blue. And then where the lamp was, you'll see the chemicals are a little darker. These are chemicals that have reacted with light. What's happened is that the energy from the photons have given the chemicals some energy to start some chemical reaction. And what you'll notice is that this chemical reaction makes these chemicals much darker than the original ones. We soak this into some solution to wash away the original chemicals, and you get what's called a negative image. We call it a negative image because as we wash everything away, we just have the black area of where we had our bright photons. So here, it's called a negative since we have a bright lamp that's white here and a dark lamp here in our negative image. It's the opposite of what we originally did. So if we go back to see what this looks like in practice, if we have our bowl of fruit that we saw earlier, and we have a camera next to it, it's going to take a picture of this bowl of fruit. And it's going to image it onto our film we have back here. Click. And you'll see we get a nice image on our film. And again, our negative image is just reproducing what we originally saw, here just in black and white. And what you'll notice is that this bright spot in the kiwi right here shows up dark in our negative image, and vice versa. Now this is a lot like what our rods are doing in our eye, but just in the opposite. So already our film is starting to be like an artificial eye you can think of. But you might sort of think about, all right, our eyes have rods, but what about cones? So if you were to take a piece of modern film and peel it apart like this, you'll notice that you have some protective layers in the front and then the back, but then you have a blue, a green, and a red layer. So you might think to yourself, I remember this from previous. Our eye also has green, blue, and red layers. And just like your eye, you can take your original rainbow of colors, and your blue layer will record all your blue light, your green layer will record your green light, and your red layer will record your red colors. And you'll smash them together to form your original image. And this is exactly what your cones are doing. So already we can use film as a way of artificially reproducing what our eye has been doing for eons now. So again, we're going to think of our film as this kind of artificial detector. And what's special about it is that it can store information, whereas our eye previously could not. But you might think to yourself, we're in the digital age, there has to be a way we can do this using technology. And thankfully, we have. It's called a charge-coupled device, or a CCD if you want to sound really cool. So a CCD is nothing more than a piece of silicon. This is the same material we use to make computer chips. We stick a wire in the back of it. And what's special about this device, this CCD, is that it interacts with light in a very special way. What happens is that when the CCD has light being shone onto it, it will then take the energy from light and convert it into electricity. So you see here that when the CCD sees light, it lights up and starts shooting electricity down this wire. So you can imagine that if you take a lot of these CCDs and smash them together, put all the wires together, if you shine light on these things, you'll see that where the CCD sees light, they'll light up and start shooting electricity. But where they don't see light, they're just going to stay off and do nothing. And you can start to interpret all these signals on your memory to start forming some sort of kind of image. And it's the same way. We see light will hit our detector. In this case, it's a CCD. And then your detector will store your information on our little drive right here. Now, if you put all these things, all these little squares together, these little CCDs, put them together, kind of like your film, you get what's called a CCD array, which is really just saying all these little squares line up next to each other. And this really looks like a computer chip, if you were looking at a modern CCD that you might have in a camera. You might think, okay, this sounds cool, it's got light, it's got electricity, a lot of cool science, but I will never see one of these in my entire life. You're wrong. This is one of those few things in this world that you are very well acquainted to. If you've ever taken a selfie, you have looked directly at a CCD. This is the thing that records every single photo you've taken on your phone and then uploaded to wherever. So you are very well acquainted with this device. And you might think, so this is our original image. We noticed earlier that our film was really great for reproducing this image, but it's kind of the opposite. The nice thing about our CCD is that it creates what's called the positive image, or just a reproduction of what we originally saw, which in just little squares. So it's nice that because our original image looks like here, our rods in our eye are showing what's light and dark, our film was kind of doing the opposite of that, which wasn't terribly convenient. But what's nice, because the CCD lights up whenever it sees light, just like your eye, it can actually reproduce what your eye originally saw. So in this way, it's kind of another perfect analog, a digital analog of what your eye is doing. And so you might think to yourself, well, what about color? So our color film, remember, it's just taking our rainbow of light and imaging those colors on a blue, a green, and a red layer. Our CCD works the exact same way. We have some blue squares, green squares, and red squares that each record different colors onto our little device, which we've called the CCD. So in the same way, by having these different layers on our device, we can record different colors of the picture. And then we just smash these things together to get our original picture, to give us our cones that we were trying to reproduce. So this is fantastic. Our CCD is a really great analog of our eye. We can actually make an artificial eye from these CCDs. If we looked at our original image, and then we look at our negative image, while the colors are inverse in our negative image, our CCD is great in that it's a positive image, but you see you have all these squares. And because you have all these big squares, our lamp doesn't really look like a lamp. It looks more like an umbrella. This gets the idea of what we call resolution. So we call one of these squares 1 pixel, which you can think of as just 1 unit of image. And we think of, if you had this kind of complicated image right here, if you had to smear it all into 1 unit, you're not going to actually see anything. It all gets kind of blurred together. So this is a 1 by 1 pixel. here. It doesn't really show much information. So we're going to pull this away. We see if we add two more pixels, 2 by 2, you start to see, okay, we have some more information shown, some blues and some grays, but nothing's really shown here. So we're going to start to kind of reveal a new image in some more pixels. Here, 5 by 5. See some blue, some grays, some whites, but still don't really see much. At 10 by 10, you start to see, all right, there's a shape of something going on. I know this part's blue, this part's white, but I have no idea what this is. And then as we get 20 by 20, we start to see, okay, this seems to be maybe some person, like a letter maybe, but it definitely has a blue region, a white region, and a black region. At 50 by 50, you can see, okay, it looks like an R with a little curly Q, but kind of just fuzzy, right? At 100 by 100 by a high resolution, you can start to see the R of resolution. And you see it has very distinct colors, very distinct lines, with this kind of nice curly Q part of it. You can see all the very fine details and sharp changes in colors at a high resolution. So we've been relating things back to our eye again and again. You might think, what about our eye? So our eye has been estimated to have about 100 megapixel resolution, or 100 million pixels. So this is a 100 megapixel image you can commercially get in a camera nowadays, and you can see your eye's pretty good. See some waves, see some colors. Great. We're now in this area of ultra-high resolution. Because we can make computer chips be so small and make those pixels themselves so small, we can actually have a 50 gigapixel image, which is 500 times better than our eye, and produce what's the largest picture resolution known to man right now. This is a photo of Dubai. We're going to zoom into this red square right here, and we're going to see what the effect of 50 gigapixels is. So we're going to zoom in. This is going to be like CSI when we say enhance. Enhance. You zoom in. Closer. 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 Even closer. Wow. Look at that. We went from all the way out here to be able to resolve this logo here. See some shining light on the hood of this car. With 50 gigapixels, you can really kind of take in so much detail that our eye can never even process, and our brain probably couldn't even process. And this is kind of the amazing thing about a CCD. We're now in the age where our artificial eyes are even better than our organic eyes. And you might think to yourself, this is great. We know our eyes are really great in the visible region right here, but we know our CCDs can do even better. But our CCDs are artificial. Can we start to look at places that our eye can't see? Maybe in these infrared and long wavelengths, or these ultraviolet X-rays that we see over here. If you've ever gone to the hospital and got an X-ray, which I hope you haven't, it means you've probably gotten injured pretty badly. But if you have, you've gotten an X-ray interaction with an X-ray detector. So what you do is you have an X-ray generator, which is some sort of source of X-rays. It images your hurt arm right here, and then you pass those X-rays through your arm, and then it images onto a detector, which is behind your arm. So this X-ray detector is just our normal CCD that we talked about earlier, but has what's called a fluorescent material on top. And this fluorescent material is just taking the high-energy X-rays and convert it into visible photons, which you already know how to work with. And these visible photons will then image this X-ray that you've commonly seen right here. This is cool. We like X-rays. We like biology. Awesome. But what about even bigger things? So if you were to ever look at the Milky Way galaxy through a telescope, or maybe you like cool images of space on the internet, you might have seen something like this. This is our Milky Way galaxy in visible light, what our eyes can see. But if you look at an X-ray radiation, you get what's called the cosmic X-ray background, which is the same image, but looking at the formation of very distant galaxies in our solar system and our Milky Way galaxy. So you'll see it looks very different because our X-rays are a very different region of energy that our eyes cannot see. You might think to yourself, how do we make these images? Well, the Hubble Space Telescope, which orbits around Earth, is really nothing more than a very fancy camera with this X-ray CCD inside, and a lot of other detectors as well. But specifically, we have these X-ray detectors that are really good at making images like this. So it's the same idea of this CCD we talked about earlier, but we're using the power of them to start to do cool science, just outside of taking pictures of food. So now that we've been able to do science with our CCDs, we're starting to see there's a new avenue of these kind of artificial detectors that allow us to make sense of our world. So we kind of take a step back and think about what is a detector. So our eye is kind of a great example of we have our detector as this thing that will interact with light. Light will hit our eye, and then our eye will then send the information from light to our brain. It would then looked at our CCD as a really good way of kind of an artificial eye. What's special about our CCD is that it'll store the information from this light in a way that allows us to take cool pictures of science and learn about our world in a more interesting way than we could have before. In this way, we can store the information from light. We can make these artificial eyes from film or CCDs. And finally, do really interesting things with these CCDs. And space is cool, one of the biggest things in the world, but we also have very tiny things in the world. And to learn more about that, I'm going to turn it over to Kimmy, who's going to talk about some of the smallest things in our universe.